Ratio scale property is, in some ways, one of the more important aspects of extensive measurement. The third motive for looking at these non-additive concatenation structures is that in the theory of conjoint measurement, one used a device of mapping the conjoint structure onto an operation on a single component. And when the conjoint structure satisfied the conditions that lead to additivity there, it turned out that that component, the structure induced on the component, was an extensive structure. Now, if you go to more general conjoint structures that are not additive in character, you can still probably carry out the same induction on a component, put an ordering on the component, but then it's reasonable to expect that that will not be additive, and you, at that point, cannot proceed with the kind of construction that we used before unless you understand how non-extensive concatenation structures behave. So it's for those reasons we want to look into this topic. I will present a definition that is due to Narens and myself, and let me first just say quite generally, what it amounts to is the same structure that we used in extensive measurement, namely a set of objects, an ordering relation on them, a relation that describes what elements can be concatenated, and the concatenation operation. And the axioms that I'm going to have I've written down here are almost identical to those of extensive measurement. There are trivial changes had to be made, but they're really very minor, except one axiom is omitted. The associativity axiom does not appear at all. What remains is the weak ordering assumption, a non-triviality assumption that there really is a distinction between at least two elements. Local definability, recall that if A and B can be concatenated and C is less than A and D is less than B, then the postulate is that C and D can also be concatenated. That's pretty much the same, a slightly different formulation than we used in the theory of extensive measurement. It's the same idea. Monotonicity, when concatenation can occur, is as before. Restricted solvability is almost the same. It's a little bit stronger because in extensive measurement we used a weak inequality here, and here we're asking for a strict inequality. Excuse me. Positivity is as before, and the Archimedean property is as before. We again state that the standard sequence is defined inductively as NA is n minus 1 copies of A concatenated with A. Now there is a point to be made here, and that is that when you don't have associativity, there are lots and lots of different possible definitions of what you mean by a standard sequence. This is only one particular definition, because you see, it matters without associativity. It matters whether I'm talking about this or whether I'm talking about this, and so on. These are all maybe different in this structure because associativity doesn't hold. It means you cannot throw away those parentheses. You've got to do things in the order indicated. However, it turns out that it is sufficient to state the Archimedean property for one particular definition of a standard sequence, and this is the one we will use. So everything is as before, except associativity is dropped. I should warn you that it takes a certain amount of time to get used to proving results in this framework. We are so used to the associativity property that it is invoked without mention in very many proofs of results when associativity is assumed. The danger, of course, is that in this situation one will invoke associativity inadvertently, and you have to really be on the lookout that you're not bringing it in some implicit fashion. The theorem that Nairns and I presented in 1976 is the following, that if A is a positive concatenation structure, any structure of this character, then there exists a homomorphism phi into a real positive concatenation structure that's of the form it's on the positive reals greater than or equal to some subset of the reals cross the reals with a numerical operation, not of course addition, but some other numerical operation defined on the set S. By a homomorphism, I mean the usual thing. The structure is preserved. That is, the qualitative inequality goes into numerical inequality, and the qualitative operation O goes into the numerical operation O dot. The idea of the proof is as follows. You use the axioms, in particular the restricted solvability axiom, to establish the existence of a sequence of elements in the structure, A sub n being a typical element, such that an is indifferent to the next higher element in the structure composed with itself. Intuitively, what you're doing is having the element an plus 1 is intuitively the half of an. That is, you combine it with itself and you get an. So that it's a descending sequence, and it also has the property that for every element in B, if you go out far enough in the sequence, it becomes smaller than that element B. So the first step is to prove the existence of such a sequence. The second step then is to look at what you get from taking the sequence, which is countable, and now make as many copies as you can of each of the elements. I've symbolized it this way. This is somewhat misleading, but let me describe it in words. We don't need symbols for it. You use the ability to make copies of these to the extent that you can. I mean, we are restricted in this system that we have only local definability, so you cannot necessarily make an indefinite number of copies, but you make as many as you can. It cannot be more than a countable number. It may be finite. You then look at the union of all of those elements, and that's clearly a countable set, but what you're able to show is that it is an order-dense subset of the structure. That puts us then in the position of being able to invoke the Cantor-Birkhoff theorem of ordinal measurement, and that establishes that there's an order-preserving numerical function phi. So we've got a function that preserves the order. And then what we do is simply construct the operation so that in the reals, we construct an operation that will preserve under phi the given concatenation operation. This seems like as though it's slightly immoral. I mean, what we're doing is generating first an order-preserving function, and then having gotten it, we construct for ourselves a binary operation which does the job. And we do it, it's the simplest thing in the world. You just, for any two numbers, x and y, that lie in the domain of where the image of A under the order-preserving function phi, and if the inverse is under phi of these two elements can be concatenated, then we define the concatenation of x and y in the numerical operation O star as simply what you get by inverting x back into A, y back into A, concatenating there, and then mapping back into the reals. So that what we're doing is as follows. Here's A, here's the the reals, or well, we'll call it phi of A, but it's in the reals, positive reals, so that the phi function is mapping in like this. We pick an x and we pick a y. We look back through the mapping to whatever element it was that mapped into x. We look back in the mapping to what mapped into y. If those two can be concatenated, then we concatenate them. That forms an element here, and we map back in there, and we call that x circle dot y. And that has the desired property of preserving the operation. Now, one can wonder how unique all of this is. And once again, the uniqueness question has, in a way, two parts to it. You recall when we were talking about extensive measurement, we asked about the uniqueness when the two homomorphisms go into the same numerical operation. There we were using plus. There was also a question about going to other numerical operations, which was a separate issue. And the uniqueness theorem that I'm going to state here concerns two homomorphisms into the same operation. So I assume phi and phi prime are both circle dot homomorphisms. That is, they use the same numerical operation. And let me further assume that they have the same image. That is, they map onto the same set of numbers. The assertion is that if we can find any element little a in the structure such that the two homomorphisms agree at that point, then they are in fact identical. Now that statement is also true of the homomorphisms in extensive measurement. We didn't formulate the axiom, or the uniqueness result that way. What we said was that any two homomorphisms into the additive reals differed only by a positive constant. But if we then add the assumption that they agree at some point, that forces that positive constant to be 1, in which case they're identical. So that this form of uniqueness followed from the other one. Now, what this form of uniqueness doesn't do is to tell you, if you have two homomorphisms into the same operation that don't agree at a point, how they relate to one another. And we're going to want to come back to that question, although we'll only deal with it in somewhat restricted domains. To get at that question, it turns out that the concept of an automorphism of a structure is quite critical. An automorphism, intuitively, is a mapping of the structure onto itself that preserves all of its properties. That is, the structure, if it has an automorphism other than the identity, it means that the structure exhibits certain symmetries, that that you can look at it and through the automorphism, and everything looks the same, even though you've mapped different points into every point into a different point. The formal definition is as follows. It's a function from A into A that is one-to-one and onto. It preserves the order, and moreover, it preserves the operation. That is, theta of AOB goes into theta AO theta of B. So it looks like a homomorphism of the structure into itself, but it's stronger than a homomorphism because it's one-to-one and onto, which makes it an isomorphism. So what we're saying is an isomorphism of the structure with itself is called an automorphism. Now, Cohen and Nairns proved that if one has a positive concatenation structure with a homomorphism phi into the operation circle dot, then, and if theta is an automorphism of that structure, then the function that is obtained by first applying the automorphism and then the homomorphism is again a circle dot homomorphism of the structure. If graphically, if this is A and this is the reals with the operation circle dot on it, you have the homomorphism phi, and you have in A mapping an automorphism theta. And what's being said here is that if I first apply theta and then apply phi, that will also produces this mapping, and that mapping phi after theta is in fact again a circle dot homomorphism. And the second part is that if you have two circle dot homomorphisms, phi prime and phi, such that their images are exactly the same, then there exists an automorphism theta such that phi prime is phi applied to theta, so that the uniqueness is captured in these positive concatenation structures by knowing the automorphisms of the structure. So this puts it far more closely in the framework that we're used to, namely a characterization of how two homomorphisms into the same operation are related to one another. Now it differs somewhat because, after all, in the theory of extensive measurement, we showed something of the form phi prime was alpha, where alpha is a number, times phi, so that what we were saying there was that we could characterize in the domain of the reals a certain class of transformations that relate the two homomorphisms. What we're saying here is not a transformation in the reals, but rather a transformation in the positive concatenation structure, in the qualitative structure that causes the two homomorphisms to be related. These are distinct notions, and what we will be doing a little bit later on is restricting ourselves to certain types of positive concatenation structures where we in fact can represent the uniqueness in this way we were used to, the ratio scale uniqueness that we're used to from extensive measurement. The automorphisms of positive concatenation structures turn out to be far more regular than one had any reason a priori to expect. And that is what I want to next talk about. And the story begins with the following theorem that's reported in Cohen and Nairns in 1980. Suppose theta is an automorphism of a positive concatenation structure, and that for some element in the structure A, one of three things could happen. Either the automorphism maps A into itself, or it maps A into something that is larger than A, qualitatively larger, or into something that is qualitatively smaller. The remarkable thing is that if it maps A into itself, then one can prove that theta must be the identity homomorphism. If it maps it into something larger than A, then for every element in the structure, the automorphism maps it into something larger. And if it maps it into something smaller for one element, then for all elements, it maps it into something smaller. So that there's an enormous regularity vis-a-vis the ordering relation. We will now make use of that regularity in the following fashion. Let G denote the set of all the automorphisms of a positive concatenation structure, and let star denote function composition. That is to say, eta star theta applied to the element A is equal to theta applied to A and then eta applied to that element. And on this set G of automorphisms, we define an ordering relation, which I'll denote by the same symbol as the order in the concatenation structure, but with a prime. And I'll say that automorphism theta is at least as large as automorphism eta if and only if, for some A, theta A is at least as large as eta of A. And by the fact that inverses of automorphisms exist, this becomes the statement eta inverse theta of A is greater than A. And we know by the preceding theorem that this is quite independent of the choice of the element A. If it's true of one element, it's true of them all. So that this is a well-defined definition, and it establishes this ordering on the set of automorphisms. Actually, under function composition, the set of automorphisms is well known to form a group. That is, the identity map is the identity element of the group, and there are inverses for every automorphism because they're one-to-one and onto functions. With that notion of an ordering on G, we have the following rather remarkable theorem due to Cohen and Nairns, and that is that for a positive concatenation structure, the system consisting of the set of automorphisms, the ordering, and the composition operation is in fact an Archimedean ordered group. Moreover, if there is at least one automorphism other than the identity, that is, if the automorphism group is non-trivial, then the operation in the positive concatenation structure must be defined on all possible pairs of elements. That is to say, it must be a closed operation. So the gist of this theorem, given that now that we know that we're getting an Archimedean ordered group, is that the automorphisms have to be isomorphic to a subgroup of the additive reals. That's what Holder's theorem tells us. Now, there's one thing that's very important to understand about this theorem. What it is saying is if the automorphisms exist, then they're very regular, which must in turn mean that the positive concatenation structure itself has a great deal of regularity about it. On the other hand, one of the possibilities for certain of the positive concatenation structures is that the set of automorphisms has only one element, namely the identity element, in which case then this theorem has no force at all. The structure of the set of automorphisms is trivial. It's simply the identity automorphism, and there is really no constraint being established. So that what we have is the following situation. The positive concatenation structures can be divided into two sets. Those that have non-trivial automorphism groups, which must of necessity then be highly regular structures because of this theorem, and those that have only the identity automorphism, which structures are undoubtedly fairly irregular, and we don't really know anything about them. At the present time, there is, as far as I know, no results available about the positive concatenation structures that have only the trivial automorphism group. The remainder of the discussion in this lecture will be concerned with certain of the ones that have non-trivial automorphism groups. Now let me sketch the proof of this theorem. There's only one part of it that's the least bit tricky. The establishing that it's a group it's well known. It's very easy to establish. The monotonicity property is also very easy to establish, and the only real question is whether the group is Archimedean. And to show that, one can proceed as follows. Let iota stand for the identity automorphism, and select an automorphism that is greater than the identity. This is on the assumption that there is an automorphism different from the identity. If you happen to pick the one that's less than it, then take the inverse of it, and that will be greater. Now, suppose it is true that the Archimedean property fails. That is, that we can find some automorphism such that it is strictly greater than theta applied to itself n times successively, and I'll denote that as theta to the n. So that theta to the n means theta applied to theta to the n minus 1. Suppose we have an automorphism that exceeds that for every n. That's what a violation of the Archimedean property would be in this in this group of automorphisms. Now select an element in A. We know that because by hypothesis theta is greater than iota, it means theta of A is greater than iota of A, which in turn is equal to A. So by restricted solvability in the positive concatenation structure, we can find a B such that theta of A is strictly greater than AOB. Now notice if I apply theta to this inequality, I have theta applied to theta of A is greater than theta applied to AOB because order is preserved under the automorphism. And this, of course, is theta of A, O theta of B. And on the right, the left-hand side is theta squared of A. Repeat that over and over again, and by induction you see that you have theta to the nth of A is strictly greater than theta to the n minus 1 of A concatenated with theta to the n minus 1 of B. By theorem 4, we know that since theta of A is greater than A, that same relationship holds with B replacing A for any B, so this holds. So now taking this relation, we have that written down here. We easily see by induction on this that theta of n minus 1 of B is greater than B, so we can replace that by that using monotonicity. And on working an induction hypothesis that theta of the n of A is greater than NB, the induction hypothesis gives us that this is greater than that, and that, of course, by the definition of NB combines to that, proving that theta to the n of A is greater than NB for all n. Since by hypothesis we had taken the zeta automorphism to be greater than theta to the n for all n, we conclude then from this that zeta to the A is greater than NB for all n, which is a contradiction in the original positive concatenation structure, a contradiction of the Archimedean axiom. But since we've assumed the Archimedean axiom, this means whatever led us to this it must be false, and what led us to this, of course, was the assumption that the Archimedean axiom was not holding in the group of automorphisms. And so that proves the theorem 5, that we're dealing with an Archimedean ordered group of automorphisms. All right, now I want to turn to the question of the class of positive concatenation structures that wind up having a representation that looks like a ratio scale. The results that I will be presenting are sufficient conditions to getting a ratio scale. They're not necessary. That is, there may be other structures that have ratio scale representations than these, but this is a class that does. We'll say that a positive concatenation structure in the reals, actually the positive reals, with the numerical operation circle dot, we'll call that a unit structure if and only if there exists some real function f such that the operation circle dot is of this structure. X circle dot y is a function, the function f, of the ratio of x to y, then that's multiplied by y. Now, why would we be interested in this kind of a structure? Well, you see that if you make a ratio scale change in the variables, say I increase them by the amount alpha, alpha is a number greater than 0, and I look at alpha x concatenated with alpha y, then in this form you have f of alpha x over alpha y, and then alpha y here. But the alpha in here cancels, so this looks like f of x over y and y here, all multiplied by alpha, and that is just alpha times x circle dot y. So a change of scale by alpha is invariant under this particular operation when it is of this form. Now we know, for instance, that the additive cases of this character, if we're dealing with additivity, that can be written as x over y plus 1 times y. And that's of this general form. But there are, of course, many other unit representations than additivity. In fact, for every real-valued function, actually I mean real increasing function, any one of them will generate a binary operation that has the appropriate ratio characteristic. Now the question is, what positive concatenation structures have this kind of a representation? The first thing I want to do, however, before I mention that, is to talk about the uniqueness of that representation. This theorem, number 14 in the chapter, asserts how they're related. Suppose that we have a positive concatenation structure which has two unit representations. Phi maps the concatenation structure into a representation which involves the function f. Psi maps it into a representation that involves the function g. The assertion then is that they're related in the following fashion. There are two positive constants, alpha and gamma, such that phi is a power transformation of psi, and f and g are related in the following fashion. F of x is equal to g of x raised to the power 1 over alpha, and then g itself raised to the power alpha. So that characterizes how they relate to one another. In order to discuss some of the positive concatenation structures that have this type of representation, we need to introduce several new concepts that are fairly important. The first of these is a device, a qualitative device, to ensure that the representation will be onto the positive reals. It's a concept that has arisen in the study of the real number system, but can be generalized to any ordered structure. And the name it goes under is Dedekind Completeness. We'll say that an ordered structure is Dedekind complete if for every non-empty bounded subset there is a least upper bound to that subset. Now, the well-known examples are of this concept are in the reals. In particular, the set of real numbers, or the positive reals, is Dedekind complete, whereas the rational numbers are not Dedekind complete. For example, if I look at the rational numbers m over n, such that m over n squared is less than 2, or put another way, that m over n is less than the square root of 2, that's a bounded set, clearly. It's bounded by the real number square root of 2. It does not, however, have a least upper bound. That is, a least upper bound in the rationals. Because if I take any rational p over q that bounds the set, that is greater than the square root of 2, it cannot be equal to the square root of 2 because the square root of 2 is not rational. If I take any such rational and say, well, that's the least upper bound, I immediately know I'm wrong, because between any real number and a rational number greater than it is another rational number. And so there will be no least upper bound. What we're doing by assuming Dedekind completeness in the positive concatenation structure is essentially eliminating the possibility that the rationals would be, or something similar to the rationals, would be a representation of the structure. We're tending to, as you'll see, to actually force the representation to be onto the real numbers, which is typical of most models of attributes that are used in the physical sciences. We'll say that a positive concatenation structure is a fundamental unit structure, FUS, if it meets two conditions. The one we just talked about, the positive concatenation structure should be Dedekind complete, and a second condition, which turns out to be very important, called one-point homogeneity. And this says that for every pair of elements A and B in capital A, there exists an automorphism that maps A into B. That forces an enormous number of automorphisms on the structure, which means that it forces a great deal of internal symmetry on the structure, because you can map from any point to any other point with an automorphism. That's what this is asserting. The resulting theorem is that if we're dealing with a fundamental unit structure, then it has a unit representation in which the mapping into the reals is actually onto the reals, and it is also a ratio scale. So this is a generalization of extensive measurement in that it ends up with a ratio scale. It ends up with a formulation of the operation that is of this character, and the mapping is onto the positive reals. So it's a genuine generalization of extensive measurement that continues, however, to have that very nice property of there being a ratio scale. Now, the important added constraint beyond the conditions of a positive concatenation structure, the important constraint is that we're dealing with a structure that satisfies one-point homogeneity. And it seems desirable to attempt to understand what that means a little bit better. And there is a theorem that in the presence of Dedekind completeness and positive concatenation structure gives two alternative characterizations of what one means by one-point homogeneity. The first of these is that, and this is probably the more interesting of the two, is that the n-copy operator, when applied to a concatenation, is equal to n copies of A concatenated with n copies of B. You may recall that in the lecture on extensive measurement, we several times ran into the need for this particular relationship, and in that context we were able, by means of associativity and commutativity, to establish that it would hold. Here we're saying that this same property is equivalent to one-point homogeneity, and we're not, of course, assuming either commutativity or associativity to get it. It's a very strong condition on the n-point or n-copy operator. In fact, another way of saying what this property is that it's saying the n-copy operator is itself an automorphism. You see, if I define theta sub n to mean theta sub n of A is equal to n copies of A, then what this is saying is that theta sub n is an automorphism. An alternative way of characterizing one-point homogeneity is to say that the group of automorphisms is dense. That is, that we cannot choose a single automorphism and say that all of the other automorphisms are formed by simply making function composition of theta on itself. That they're not generated in a discrete fashion as this would be. This forces the automorphism group through Holder's theorem to avoid looking like the rationals. Rather, it looks like the subgroup of the reals that is not the rationals. Let us turn now to another major use of positive concatenation structures, and that is in connection with non-additive conjoint structures. You recall that in the work on additive conjoint measurement, we induced an operation on the first component that carried the information about the nature of the ordering over the Cartesian product and allowed us to use, in the simplest case, to use Holder's theorem, and in the more complicated case of restricted solvability, we had to use the theorem about the additive representation of extensive structures with a partial operation. Now what I want to do is talk to you about far more general conjoint structures and ask whether we can do the same kind of thing as we did in the additive case. The more general definition that we will use is the following. We again have a Cartesian product. Incidentally, the notation in this chapter is changed. Before we used A1 cross A2. Here I'm using A cross P. An ordering relation on the Cartesian product and two distinguished elements, A0 in the first coordinate and P0 in the second coordinate. And we'll call that a conjoint structure that is A-solvable relative to A0, P0, which is a form of restricted solvability. We're not asking for nearly as much solvability as we tended to in the previous additive cases. We're having special solvability relative to these elements. The conditions are, again, that we're dealing with a weak order. No surprise there. We're assuming independence. No surprise there. The solvability is just that is necessary to define an operation on the first coordinate. And it's just as it was in the additive case, a mapping from the first coordinate to the second called pi, mapping zeta from the Cartesian product to the first coordinate, and they're defined in the following fashion. The pi of A is that element in the second coordinate which, coupled with the zero element A0 on the first coordinate, exactly matches A on the first coordinate with the zero element P0 on the second coordinate. And zeta of AP is that element in the first coordinate which, coupled with the P0, exactly matches AP. So it's a way of taking the pair AP and placing it in something that is equivalent to it entirely in the first coordinate. We also require a density assumption that is fairly weak, namely that if we hold the second coordinate at P0 and A is strictly larger than B, then we're able to find something in the second coordinate that places the value BP right between these two. And finally, of course, there's an Archimedean axiom. It's the usual version, and I won't specify it in detail. Now, exactly as in the case of the additive conjoint case, we define the operation on the first coordinate. I'll here call it star sub A, and it's exactly the same definition as before. We wrote it this way previously. A star sub A B is that element that is, when associated with the 0 element of the second coordinate, is balanced by A and the image of B in the second coordinate. Or another way of stating it is that it is equal to the zeta function applied to A and pi of B0. It's exactly the same definition. I shall let script I of A be the system that consists of the base set A, the induced ordering on that first coordinate, and the operation just induced. If A plus is the positive elements, positive relative to this artificial 0 element or distinguished element that we've assumed exists, then I'll use as script I A plus the restriction of I sub A to the positive elements. And the theorem, I've combined two theorems into one here. The first one says that suppose we're dealing with a solvable conjoint structure satisfying the axioms we just discussed, and suppose that the element A0, P0 is not maximal in this conjoint structure, then the structure I sub A plus, that is the induced ordering on the first component, the induced operation on the first component, but restricted just to the positive elements, is a closed operation and forms a positive concatenation structure. So what we're inducing from this conjoint structure on the first coordinate is a positive concatenation structure. That is very strong evidence that we've captured a very reasonable type of structure in the definition of a positive concatenation structure. The fact that that's what pops out from the conjoint structure of a very general character is very reinforcing that that's a sensible definition. The second theorem, 20, is the converse, which says if I have a positive concatenation structure with a closed operation, restricted only to the extent that it is possible to adjoin to that structure what amounts to a 0 element in a consistent fashion, which is a slightly technical matter, but I think one can get the idea of what's involved. It has to be attached in such a way as to not violate the ordering relations and at the same time have the property that A star A0 should be equivalent to A and the other way around. A0 star A little a should be equivalent to A. If the positive concatenation structure admits that adding of a 0, then one can construct a conjoint structure whose induced structure, induced as I've described over here, is in fact isomorphic to the given positive concatenation structure. The gist of the converse is that nothing more restrictive than positive concatenation structure falls out of this induced operation from the conjoint structure. So that it is just exactly the right idea that is needed to study the conjoint structure, the general class of conjoint structures, and to reduce their analysis to the analysis of a concatenation structure. The next, well, let me go to there's a corollary then to this theorem, which you would anticipate, since we know that we can represent positive concatenation structures in the reals with some sort of a binary numerical operation. The fact that we're getting those kinds of structures out of the conjoint structure strongly suggests that we ought to be able to give a numerical representation of an arbitrary conjoint structure. And the corollary reads that if A0, P0 is a minimal element of the conjoint structure, then we can find a mapping of the first coordinate, phi, of the first coordinate into the reals, mapping psi of the second coordinate into the reals, and a binary numerical operation, which I'll again denote as circle dot, such that three things are true. The minimal elements map into 0. They act like identities vis-a-vis the operation, And third, the operation is order preserving. That is, if I have the inequality AP greater than or equal to BQ, that is equivalent to the numerical inequality phi of A with a circle dot operation to psi of P is greater than or equal to phi of B circle dot psi of Q. And of course the additive case is when circle dot is plus. But this is a general case. It's saying that we're going to be able to represent any conjoint structure by a binary numerical operation on scales on each of the separate coordinates. This is then a generalization of the theorems that we talked about in the additive case. The additive case is very simply related. Let me state the theorem. Theorem 21 says that if we have one of these solvable conjoint structures, then that structure satisfies the Thompson condition, which you recall is the double cancellation property for indifference. That is, the Thompson condition is AX is indifferent to FQ and FP is indifferent to BX. Then we can cancel out the X's and cancel out the Q and conclude AP is indifferent to BQ. So that the Thompson condition on the conjoint structure is exactly equivalent to the induced operation being associative. That gives us a quite adequate understanding of the general structure of conjoint measurement and how it relates to the induced operation. In the second lecture on dimensional analysis, we will return to these kinds of structures, in particular the unit structure representations, and pursue further some of the properties of general conjoint structures when they're interlocked with unit structures on one or both of the components.